I'm here to give you a 201 talk on breaking free from the client-server model. All right, so let's get started. First, by culling back all of the noise in the background, and let's focus for a moment on what the client-server model even is. Through this, we'll rebuild the graphic and hopefully with it, your understanding of the concepts at play as a whole. So what is the client-server model? Well, today, only a few companies are responsible for serving up most of the web. For the most part, all our data routes through their servers. If you want to view a video, send a message, collaborate with remote teammates, or do anything on the web at all really, you're going through someone's central server. In the client-server model, generally, if you want some data, you must know where it is. Think of how you would share a video on your favorite video platform. You'd likely just share the URL to the video, also known as the location of the video. A major drawback of the client-server model is that a single outage can take entire services down. Scaling can be very expensive. These expenses don't always, maybe not even usually happen linearly. Content creators are often completely locked to a few platforms like YouTube, Instagram, and other similar platforms. Those can be subject to a whole host of rules and regulations as well, far more restrictive than what your local government might allow, and you have no say in when or how these rules change. Breaking free from the client-server model means rethinking how the web works as we know it today. Love it or hate it, I believe there's a clear and strong argument for how the Web 2 model, referring to the client-server model, can be improved. What do we call this new model? This new model is referring to the distributed web. So let's talk about that and how IPFS fits in. IPFS creates mathematically generated fingerprints for data called content identifiers, or CIDs for short, and is fundamental to how IPFS works to give us content addressing, breaking us free from location-based addressing. If you're requesting data by its CID, you can also verify it's the correct data as you have the hash of the data you're expecting baked right into the CID. So you don't have to trust who's sending it to you, as you can simply run the hash function. If you want to share a web page, an image, a video, or an article, you know that if you send that CID to your friend, they can download the exact same version of the data you also saw. As long as at least your node or someone else's has a copy, you can share it. Now, transparently, the network can find new routes around problems. Problems in this case can be outages. This can work with entire internet outages as well in certain countries, as long as some node on the local network has a copy of the data. Think about the client-server problem of when you create a popular app and your traffic explodes. That situation is effectively flipped on its head with IPFS, resulting in what we call negative bandwidth scaling costs. If a bunch of nodes are attempting to download your CID, they'll be automatically resharing that CID as well. So while your traffic explodes from people sharing your CID to each other, those very same people are helping send the data itself to their friends or colleagues automatically. So effectively, the more popular your CID is, the easier it is for people to retrieve the data from some other node that might be more local to them. This property is very important to the interplanetary aspect of IPFS. If someone on Mars had a piece of data that they originally retrieved from Earth, then another Mars user shouldn't have to wait to retrieve the same data from Earth. The network should automatically figure out that there's another node on Mars willing to serve that data. Content addressing and the distributed web helps us unlock such a future on the network level transparently.